Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 3. In Unit 5, we are studying about terpenes. In Lecture 2, we are going to study about terpenes, classification and biosynthetic pathways. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at the various topics that will be covered in this session. We are going to study about the classification and biosynthetic pathways. In the classifications, we are going to study about hemiterpenes, monoterpenes, sesquiterpenes, diterpenes, sesterterpenes, triterpenes, tetraterpenes, polyterpenes. We are going to study about the biosynthetic pathways also for the formation of all these kind of different terpenes. We also will be studying about irregular terpenoids and monoterpenes. In this session, we are going to study about terpenes, classification and biosynthetic pathways. Here is the broad classification of terpenes. Depending on the number of carbon atoms or the number of isoprene unit, they are actually classified into various types. The first one is the hemiterpenes, which contains only one isoprene unit. If there are two isoprene units are there, those compounds are called as monoterpenes. Sesquiterpenes actually have three isoprene units. So we can actually multiply the number of isoprene unit with 5 leads to the number of carbon atoms that will be present in that particular group. So sesquiterpenes generally has 15 carbon atoms. Diterpenes actually have 4 isoprene units or 20 carbon atoms. Sesterterpenes have 5 isoprene unit or 25 carbon atoms. Triterpenes have 6 isoprene units and tetraterpenes have actually 8 isoprene unit. Polyterpenes generally have large number of isoprene unit, that means they have more than 40 carbon atoms. And here are all the example compounds which are present in different types of classes. Say for example, some examples of hemiterpene include tiglic acid, caffeic acid, isovaleric acid, etc. Monoterpenes are parathymine, camphene, limonene are some of the examples. And in the case of diterpenes, we have abatic acid, taxol, phytol, etc. And in the case of sesquiterpenes, we have curcuminol, vernodolol, like that. These are basically isoterpenoid compounds. And when we talk about the sesterterpenes, we have sesterstatin, Peruvian, etc. And in the case of triterpenes, we have stigmasterol, citosterol, etc. And in the case of tetraterpenes, we have carotene, crocin, lycopene, etc. And rubber and gutta percha are examples of polyterpenes. So this is the broad classification of terpenes. We are going to look at each one class separately. Let us look at the brief overview of the different classifications. Mono and sesquiterpenes are basically present in essential oils. Actually, they are low boiling compounds, so they are highly volatile, and these compounds are generally obtained from the sap and the tissues of plants or trees. So the mono and sesquiterpenes are low boiling or highly volatile substances, and they are obtained from the sap and the tissues of plants or trees. When we talk about the di or triterpenes, these are not steam volatile. That means these compounds are having high boiling point, and these compounds are generally obtained from the gums and resins of plants or tree. So depending on the place where we are isolating, we are going to get different types of terpenes. And when we talk about the tetraterpenes, especially the carotenoids, these are all the main pigmentation agents. So they have different colors like yellow, orange or red color. And as we study later in this session, we will be looking at the different colors produced by different types of carotenoids. And these are mainly distributed in the animal kingdom. And carotenes with the molecular formula C40H56 as the general formula, these compounds are present in actually plants. So, some of the carotenoids are mainly present in animal kingdom and few carotenes are present in plants. And natural terpenes generally have a molecular formula C5H8N. So, this is the general formula of terpenes. Let us start with the first one, which is the hemiterpene. So, the hemiterpene is basically the simplest unit, or as we have seen, this has only one isoprene unit. In fact, isoprene itself is classified as a hemiterpene, and some other examples include tiglic acid as shown here, and isovaleric acid, isoamyl alcohol, senesioic acid are some of the examples of this hemiterpenes. So, the isoprene unit we have seen in the previous session also, what is the isoprene rule and what is the basis of that. So, the isoprene unit, which is a very low boiling, highly volatile substance, is the one based on which all the terpenes are formed biosynthetically. And here is the example, like 5 carbon units that are present are basically the hemiterpenes. Here we have 1, 2, 3, 4 and 5. The tiglic acid have 5 carbon, and in the case of isovaleric acid also we have 1, 2, 3, 4 and 5 carbon unit, and isoamyl alcohol also has 1, 2, 3, 4 and 5 carbon unit, and senesioic acid also has 5 carbon unit. So, all these compounds belong to hemiterpene class. And when we talk about the biosynthetic pathway for the preparation of or the formation of these kind of terpenes, two basic units are the one which are involved in the formation of these kind of isoprene derivatives, or the tiglic acid or angelic acid, isovaleric acid, etc. are formed from these two starting materials. So, here what happens is we have actually seen the IDP or the isopropene unit that is responsible for this starting material as the biosynthetic pathway, and this is the dimethyl unit. This also we have seen in the last session. So, here what happens is there is a prototropic tautomerism takes place between these two units. That means actually one hydrogen is shifting from one place to another place. So, here we have the CH2 double bond unit here, and one hydrogen actually shifts from this particular carbon, and then we get a double bond on this particular carbon. So, there is a single hydrogen atom shift takes place, and this transfer is actually called as a prototropic tautomerism, and this is responsible for two types of starting materials. When we talked about the biosynthetic pathway, this IDP and DMA DP are the starting material for various terpenes, and they can be formed by a simple hydrogen shift. And the next class is the monoterpenes. So, the monoterpene basically consists of two isoprene unit, and they have a molecular formula C10H16. And the monoterpenes may have different structures. For example, they may be linear or acyclic one, or they may contain rings. When we talk about rings, they may be monocyclic ring or a bicyclic ring or a tricyclic ring. So, here are the examples of the various monoterpenes. Myrcene is an example of a acyclic system. So, this is shown in the blue color, and alpha terpene is the one with the monocyclic system, and alpha pinene is a bicyclic unit. We have two rings that are present in the alpha pinene. And if we recollect from the gem dialkyl rule, this myserine and alpha terpene have the gem dialkyl unit outside here, especially myserine does not have a cyclic system. So, we do not talk about the gem dialkyl rule here, but in the case of alpha terpene, the gem dialkyl group is present outside of the ring, and in the case of alpha pinene and tricycline, which are bicyclic and tricyclic system, the the 6-membered ring is stabilized by the presence of a gem dialkyl group here. So, in the case of alpha pinene, we have a gem dialkyl unit which gives stability. Similarly, for the tricycline, this gem dialkyl group gives stability to this ring. So, this is how we can actually explain the stability of these compounds based on the gem dialkyl rule, and the monoterpenes are basically having 4 different structures. And when we talk about monoterpenes as well as the monoterpenoids, terpenoids means they contains oxygen additionally. These are basically the isoprenoid produced from geranyl diphosphate or GPP. So, we will look at the biosynthetic pathway a little later. And all these monoterpenoid compounds contain various oxygen functional moieties. Say for example, when we talk about an alcohol unit, nerol or geraniol has a hydroxy unit that is present in their structure. And when we talk about carvone, the carvone is having a carbonyl unit or a ketone is present, and linyl acetate contains a ester unit. So, these are all the various oxygen derivatives. And when we talk about eugenol, the eugenol has a phenolic unit and a ether unit. So, these oxygen derivatives are basically the monoterpenoids, and the different types of oxygen functionalities are present in these kind of compounds. So, here are some examples of the monoterpenes. So, the common open chain examples include myrcene, citral, geraniol, lavandulol and linolol. The structures are given here. Citral structure is given here. Citral has a aldehydic unit, linolol has a hydroxy unit, lavandulol contains a hydroxy unit, geraniol also has a hydroxy unit. So, these are basically the terpenoid derivative, monoterpenoid derivatives, and limonene is basically the hydrocarbon. So, this is a terpene, monoterpene, and menthol has a hydroxy unit, thymol has a phenolic unit, perialdehyde contains a aldehydic unit. So, these are again some of the monocyclic systems which represents the monoterpenoid compounds. So, we have the open chain or acyclic systems, and we also have a monocyclic system. So, these are some of the examples of various monoterpenes and terpenoids. Let us look at the biosynthetic pathway. So, we have seen that hemiterpenes are basically formed from the DMA-DP or IDP by a simple hydrogen shift, and these two units combined together, that means DMA-DP and the IDP, these are all the two basic simple monomer unit combined together to give geranyl OPP. So, this geranyl OPP actually, so the reaction how it occurs is actually given here. There is a hydrogen which is lost, and when there is hydrogen is lost, the bonded electrons are shifted towards the linear system, and the double bond is shifted towards, or the double bond attacks the nearby DMA-DP group, and the OPP group is lost. That leads to the combination of geranyl OPP. So, here when we talk about the head and tail, so this is basically the head unit that is present, and because the methyl group is here, so this is the head unit that is present, and in DMA-DP this is the tail unit. So, the head to tail combination leads to the formation of geranyl OPP. So, from this various monoterpenes are actually produced. So, biosynthetically how the reaction actually proceeds is the head and tail combination. So, when the hydrogen is lost, that leads to the shift of bonds, and this is the starting point for the formation of geranyl OPP using by the biosynthetic pathway. And of course, this geranyl OPP can further react with another IDP unit to give the tri isoprene derivative. So, we will look at the next biosynthetic mechanism. We will look at more about this particular reaction. So, here the linear head to tail coupling of the IPP with its isomer leads to the formation of geranyl OPP, and all the monoterpenes are formed from the geranyl OPP. The next we are going to see about the bicyclic monoterpenes. So, these bicyclic monoterpenes are basically classified into various depending on the size of the second ring, they are classified into three major groups. One is all the monocyclic all the monoterpenes contains a 6-membered ring, and the second ring may be a 3-membered ring, 4-membered ring or a 5-membered ring. So, based on that we have 3 different bicyclic systems. So, here are some of the examples that is given here. So, Thajuone is an example of 6 plus 3 system. So, we have a 1, 2, 3, 4, 5 and 6. So, this is a 6-membered ring, and we also have A, B and C. So, this ABC is the 3-membered ring. So, 6 plus 3 or the 6-3 fused system is the example of a bicyclic system, and Thajuone is an example of that. And here again, if you look at the gem dimethyl group is kept away from the cyclic system. And alpha pinene is an example of 6 and 4 system. So, here we have the 1, 2, 3, 4, 5 and 6. So, we have a 6-membered ring, and we also have a B, C and D. We have a 4-membered ring. So, this bicyclic system contains 6 and 4 rings, and here we have a Borneol, which is a 6 and 5 combination. So, here again we have 1, 2, 3, 4 and 5, 6. So, this is a 6-membered ring, and we also have A, B, C, D and E. This is the 5-membered ring. So, 6 and 5 combination is also there. So, these are some of the examples of 6-3 combination, 6-4 combination and 6-5 combination. That means the bicyclic monoterpenes are shown here. Let us look at the terpene biosynthesis, especially the alpha terpeneol cation. So, we have already seen that geranyl pyrophosphate is the starting point for most of the monoterpenes. So, how the other terpenes are actually formed, we are going to see. So, here the geranyl pyrophosphate undergoes a isomerization reaction. So, what happens is there is a cis trans isomerization actually takes place. So, this is the trans isomer, and this is converted into the cis isomer, and from this cis isomer we end up with the alpha terpenyl cation. Here we are only talking about the skeletal structures. I am not going to write about all the valency of each carbon. We are only going to look at the skeletal structure of all these compounds. So, from this particular cation, this is what is the alpha terpenyl cation, we get different types of systems. For example, this can lose a hydrogen atom is here. Once this hydrogen is lost as a proton, we end up with a limonene moiety. So, we have a double bond here. The double bond is formed here by the loss of a proton. So, this is one type of elimination that leads to limonene skeleton, and we can actually undergo this carbocation can actually attack this particular double bond, because this is a electron rich system, this is a electron deficient system. So, this actually can attack this double bond, and depending on the place where it attacks, we can actually get a more stable carbocation. So, if it attacks this particular carbon, then this particular carbon, the quaternary carbon actually becomes the carbocation most stable. So, here this becomes a tertiary carbocation. So, once the carbocation actually attacks this double bond, we end up with the most stable carbocation. So, from this this carbocation can actually lose hydrogen atom from 2 different places. One, it can attack from it can lose a hydrogen atom from the terminal carbon. So, we end up with a beta pinene. The double bond is formed in the exocyclic fashion, or there is also another hydrogen atom which can be lost here. So, as a proton, so that leads to alpha pinene. So, from this tertiary carbocation, we can actually get 2 different final product, that is alpha and beta pinene can be formed. So, this is how the alpha terpeneal cation can leads to 3 different types of monoterpenes. And here again additional reactions are shown here, which this alpha terpenyl cation can undergo. So, as I mentioned here, I am going to just talk about the skeletal structures without giving allowances to the valency. So, that is the reason you have to just look at the skeletal changes what is happening. So, we have various type of reaction. The first one is basically the electrophilic addition reaction. So, that means we have a carbocation. So, this carbocation we have a double bond here. So, this double bond attacks this particular carbocation, and this particular carbon becomes a carbocation here. That leads to the formation of terpenyl cation. So, the electrophilic addition leads to cyclisation. So, this is the first step. So, once the alpha terpenyl cation is formed, we have seen how it can actually undergo other reactions. So, let us look at the reaction number 2. So, the reaction number 2 is simply a hydride transfer reaction. So, that means this particular carbocation is now moved to the ring system. So, this is where a simple hydride transfer, that means one hydrogen comes along with its electron to this carbocation, and this carbon becomes a carbocation. So, that is how a hydride shift leads to this particular, that is terpene 4-yl cation is formed. And once this terpene 4-yl cation is formed, this is the X, that is the electrophilic site, this is the nucleophilic site. So, these two can now undergo cyclisation. So, we end up with a 3-membered ring. So, this cyclisation leads to a 3-membered ring formation and concomitant formation of another tertiary carbocation, which is quite stable. And similarly, if we start from the alpha terpenyl cation, we have different combinations or the reactions possible. So, here this is the electrophilic site and this is the nucleophilic site. In the nucleophilic site, we have 2 carbons, that means carbon number C and carbon number B. So, the electrophile can attack any one of the place. So, depending on where it attacks, we end up with 2 different types of compound. Although this is a more stable carbocation, we also have a little bit less stable carbocation that is also possible in this particular reaction. So, we have a pinane system or we have a bornane system. So, these two are formed by the nucleophilic sites at B and C. And similarly, it is also possible a Wagner-Meerwin shift that may happen. So, when a Wagner-Meerwin shift happens, actually we get a carbocation as shown here, and Fenchane type structures are basically formed by this kind of rearrangement. So, these are all the various ways by which a simple alpha terpenyl cation can lead to various skeletal structures of terpenes. And in fact, if you look at here, we have even more number of reactions that are possible. So, in the case of monoterpenes, we actually have more than 15 different types of monoterpenes can be formed simply from one alpha terpenyl cation. So, these are all the various reactions that are possible. So, biosynthetically, we can actually get different types of skeletal unit from this particular transformation. And of course, when we talk about the hydroxy unit, so what happens is there is a carbocation here and this carbocation is now attacked by a water molecule, and then that leads to the formation of the hydroxide derivative. So, alpha terpenyl or endofenchal are some of the compounds which are formed by the addition of water molecule to the carbocation. And all the other reactions are basically loss of proton that leads to the formation of a double bond. So, the double bonds, or even in some cases the cyclisation, are responsible for the different skeletal structures. The next one is iridoids. So, iridoids are basically a large group of monoterpenoid compounds. These are having a 6-membered ring containing an oxygen atom that is fused to a cyclopentane ring. So, here the fusion is always a cis-phased fusion. So, here if you look at both the hydrogen atom, in the case of iridodiol or in the case of acubin, this is the 5-membered ring is basically cis-fused. So, here the final product is basically a cis-fused cyclopenta C-pyrene ring system is called the iridoid unit. So, we have a 5-membered ring and a 6-membered ring combination that is present here. And these hydroxy unit, especially when we talk about the C1 hydroxy unit, this is quite unstable because this is basically an acetal unit, and since this is quite unstable, basically this is stabilized by the formation of glycosidic linkages. So, that is the reason most of these iridoids will have a glycosidic linkage, and this glycosidic unit actually stabilizes these kind of irido compounds or iridoids. The next class is the sesquiterpenes. So, these sesquiterpenes basically consist of 3 isoprene unit and they have a general molecular formula C15H24. And again, as similar to the monoterpenes, the sesquiterpenes may also have different structures. Say for example, they may be a linear system as shown here. Farnesene is an example of this linear system. Here we have 15 carbon unit that is present. In other words, we have a 3 isoprene unit combination leads to these kind of compounds. If they have rings, the ring may be either a monocyclic ring or a bicyclic ring or even a tricyclic ring. So, these are all the various ring structures that are possible for the sesquiterpenes. Zingiberine is an example of a monocyclic ring system. Selenine is an example of a bicyclic system. Cubibine is an example of a tricyclic system. Both the sesquiterpenes and sesquiterpenoids are formed by the farnesyl diphosphate, or the biosynthetic pathway starts from the farnesyl pyrophosphate. So, that is the C15 unit which is responsible for the formation of various sesquiterpenes. And in fact, more than 300 different types of sesquiterpene carbon skeletons are actually produced by marine, terrestrial plants and microbial source. That means both the plant and animal actually produces various types of sesquiterpene carbon skeletons. So, we can say the sesquiterpenes are the most diverse carbon skeletons that is present in terpene chemistry. When we talk about the sesquiterpenoids, actually there are 2 different class of oxygen containing sesquiterpenes are known. As we have seen in the case of monoterpene, when we talk about the terpenoid, we generally talk about simple oxygen containing compounds only. But when it comes to the sesquiterpenes, we actually have 2 different categories of the sesquiterpenoids. One compounds are generally called as sesquiterpenoids and the other compound is called as sesquiterpene lactones. So, these are all the 2 different types of compounds when we talk about sesquiterpene. As we have seen, there are diverse compounds and all this diversity came from different sets of combinations. When we talk about simple sesquiterpenoids, they have various oxygen functionalities. For example, alcohol, these farnesol actually have a hydroxy unit, and aldehyde unit is present in polygodiol. So, we have the diol unit. So, 2 aldehydic unit is present in this kind of compounds, and even we have the hydroxy unit, say for example ketone, ester, ether, phenol or other oxygen moieties that may be present. So, capsidiol contains 2 hydroxy units. So, these are examples of simple sesquiterpenoids. And in fact, we have a very unique compound called the geosmin. So, the geosmin is basically a irregular sesquiterpene, and this compound is formed from the biosynthetically formed from the farnesyl pyrophosphate, but it contains less than 15 carbon atoms. So, if you look at the number of carbon atoms, let us say start from here 1, 2, 3, 4, 5 and this is 1 6 membered, then we have 7, 8, 9, 10, 11 and 12. So, we have only C12 unit, but still this is formed from the farnesyl pyrophosphate. So, this compound is called as a irregular sesquiterpene and this is still called a terpenoid derivative. So, whenever there is a rain, we actually get the muddy smell. The muddy smell is actually due to this geosmin. So, this compound is responsible for the muddy smell what we get after the rain. So, the next major class of sesquiterpenoid is actually the compound containing a lactone ring, and these are called as sesquiterpene lactones, and most of these lactones are basically gamma lactones. So, here are the examples that are given. There are more than 6 or 7 different types of lactones are actually known, and these compounds are basically lipophilic compounds, and many of the sesquiterpenes are found in the lettuce and chicory what we generally consume. Some of the examples of the lactones, that means gamma lactones, are given here. Macronolide, guanolide, pseudoguanolide or different types of lactones that are present in the sesquiterpene lactones, and they all have the gamma lactone or the 5-membered ring that is present here. So these are very important type of compounds, and many of these compounds are used for the cardiovascular diseases, cancer, reduction of inflammation, and some of the compounds are also used as antimicrobial agent. So these sesquiterpenes are highly useful for the treatment of various diseases. And let us look at how the sesquiterpenes are actually formed. So we have seen geranyl phosphate is formed by the combination of DMADP and IDP. So the geranyl phosphate once again reacts with one more molecule of IDP. So we have a C10 unit here in the geranyl unit. We have IDP which is having a 5 carbon unit. So C5 plus C10 leads to C15. So the farnesyl OPP is actually the starting material for most of the sesquiterpenes. And in fact, this farnesyl OPP can again further react with the IDP to give the 4 isoprene unit derivative. So when we look at the diterpenes, we will be actually looking at how this combination leads to various diterpenes. So geranyl OPP leads to monoterpenes and farnesyl OPP leads to sesquiterpenes. Biosynthetically, these are all the 2 major reactions. And here again, as we see the combination, so this is basically the head unit and this is the tail unit. So the head to tail combination again happens, leading to the formation of farnesyl unit, farnesyl OPP. The next major class is the diterpenes. So the diterpenes contain 4 isoprene unit and their general formula is given by C20H32. And these diterpenes also have very low volatility. In other words, they actually have low boiling points. Some of the examples are actually given here, and these diterpenes are basically derived from the geranyl pyrophosphate. These are classified into linear, monocyclic, bicyclic, tricyclic, tetracyclic, pentacyclic or macrocyclic diterpenes depending on their skeletal core. So we have various cyclic systems that are possible in the case of diterpenes. So here is an example of a acyclic or a linear one. Phytane is an example of that diterpene, and semperene is basically a macrocyclic one because this is a very big or a huge ring. So this is a macrocyclic diterpene. Lambdane is an example of a bicyclic because we have 2 ring units. So this is an example of a bicyclic system. Taxadiene is an example of a tricyclic system. So this is an example of a tricyclic diterpene, and stimarene is an example of a 1, 2, 3, 4. This is a tetracyclic unit. So we have different cyclic systems that are possible in the case of diterpenes. And in fact, many of the useful diterpenes are formed as a diterpenoid, and some of the important compounds are retinol. Vitamin A1, as all of us know, is an example of a diterpenoid. It is very essential for our human beings, and retinol is also another because for our vision basically depends on these kind of compounds. And phytol is another compound which is a linear one, contains a hydroxy unit. So this is a terpenoid, diterpenoid, and gingolides and abatic acid, cativic acid are some of the examples of polycyclic or bicyclic, tricyclic and polycyclic diterpenoids. So here we have the carboxylic acid unit in the case of cativic acid, and in the case of abatic acid also we have a carboxylic acid unit, and the gingolide is basically having a lactone unit, and it is also having multiple lactone units, hydroxy units, etc. So this is also an example of a oxygen containing diterpenoid. Let us look at the biosynthetic pathway. We have already seen how the hemiterpenes are formed and how the monoterpenes are basically formed, and from the monoterpene we are going to see how a diterpene is actually formed. So we have seen this is a 10 carbon C10 unit, geranyl unit is a 10 carbon unit. This 10 carbon unit add with another 5 carbon IDP to give a C15 farnesyl unit, and the C15 farnesyl unit adds with one more C5 unit to give a C20 geranyl OPP is actually formed. So here this is basically a head to tail combination, so that leads to the formation of this particular geranyl OPP. So the C15 and the C5 unit combine together to give the C20 unit, which is the geranyl OPP. From that we get various diterpenes. The next one is the Sesterterpene. So the Sesterterpene actually contains C25 skeleton. The C20 core carbon skeleton is having an additional C5 head or a C5 tail unit. So this is a different type of terpenes, and many of these compounds are actually found in fungi. So this is the only exceptional case. Whatever we have seen so far, all the terpenes are obtained from either plants or animals, and this Sesterterpenes is actually found in most of the fungi, and they exist in various or a variety of forms, including a linear, monocyclic, bicyclic, tricyclic, tetracyclic or macrocyclic form framework. For example, moinosinol is actually a linear unit, and manolide is actually having a multicyclic systems, and vericolol actually has a polycyclic system. So these are some of the examples of the Sesterterpene and the terpenoid compounds. Let us move on to the next one, which is the triterpene. So the triterpene compounds have a carbon skeleton with 6 isoprene unit, and their general formula is C30H48. These are actually derived biosynthetically from a acyclic C30 hydrocarbon unit, that is the squalene. So this is the most crucial one for many of the triterpenes. More than 30,000 triterpenes are actually known, which are produced by animals, plants and fungi. So of all the terpenes, triterpene forms the major class of compounds, and we will look at what are the different types of compounds that can be produced or obtained from the triterpenes. We will see. Here we have couple of triterpenes. Polypodatetraene is an example of a triterpene. Lanostan is another example of a triterpene. Ferinolol and achiliol are some of the triterpenoid compounds, because here we have the hydroxy unit that is present in this kind of compounds, and they have here in the case of lanostatin we have 4 rings, 1, 2, 3, 4, and this ferinolol contains 1, 2, 3, 4, 5 rings. So these are tetracyclic and pentacyclic systems, and here achiliol has only 1 ring. So these are some of the examples of the triterpenes or triterpenoid compounds. And in fact, the triterpene or triterpenoid are even broadly classified into various types. As we have seen, they may be acyclic triterpenoids. Squalene is the hydrocarbon unit that may be present in all these kind of compounds. Monocyclic triterpenoids are actually, some examples include achiliol, and bicyclic triterpenoid is a oxide, and tricyclic triterpenoid, an example is a lancioside, and tetracyclic and pentacyclic triterpenoids are actually given here. These 2 classes of compound, basically we had given the hydrocarbon unit from which these different triterpenes are actually formed. So here when we talk about this classification, all these different types of compounds have the same basic skeleton as shown in these kind of grouped compounds. And the triterpenoids are basically much more complex cyclic structures. They may contain alcohol units, aldehydes or carboxylic acid units. So urosalic acid has a carboxylic acid unit and a hydroxy unit. Betulinic acid also has a hydroxy unit and a carboxylic acid unit. And we also have saponin, a different type of compounds. They have a glycosidic unit and a triterpene unit. So these are all the different types of compounds, and many of these compounds are and especially many of the complex cyclic triterpenes are produced by plants and not by animal or fungi. So, this is the major difference. Although many triterpene compounds are formed by the plants, animals and fungi, many cyclic triterpenes are actually complex cyclic triterpenes are produced only by the plants, and many of these compounds are generally used to treat various diseases in which immune system is actually involved. So, the saponin contains 1, 2, 3, 4, 5 and 6 ring systems are there. Actually, a part of this is basically an alkaloidal unit. As you can see, the nitrogen is actually the tertiary base nitrogen is present. So, this is a combination of terpene and alkaloid and glycosides. So, this is a complex compound which is produced by the plants. And steroids and saponins are a very important class of triterpenoids or triterpenes. Steroids are basically based or having a cyclopentane perhydrophenanthrene ring system. So, we have this is basically the phenanthrene ring system, and this is a perhydrophenanthrene ring system. Along with that, a cyclopentane unit is actually added. So, that is the reason these compounds belong to cyclopentane perhydrophenanthrene ring system, and all the steroidal compounds have this basic skeleton, and from this sterol various steroidal compounds are actually produced biosynthetically, and damerin skeleton is actually shown here. From this various triterpenes are actually produced, and when the plant produces the sterol, they are basically called as phytosterols. And here is the triterpene biosynthesis. The major difference between the previous terpene synthesis and the triterpene biosynthesis basically a combination of a tail to tail dimerization. So, the two FPP units actually combined in a tail to tail fashion. We have a farnesyl OPP which is a C5 unit, C15 unit, and we have another farnesyl unit which is a C15 unit. So, here the combination actually happens between this is one tail, this is another tail. So, two tails are actually combined together to give the squalene structure. So, the squalene structure is actually given here. So, the major difference between other terpenoid compound and the triterpene is basically the way in which the two OPP unit or the pyrophosphate units are actually combined. So, this is a major exception to the normal synthesis of biosynthesis of terpenes. So, here two C15 units combined together to give a C30 unit, and this C30 unit is basically the squalene unit. From the squalene we have different terpenoid skeletons. For example, prostane skeleton which is a tetracyclic ring is formed. Here we have the perhydro, this is basically the phenanthrene unit, the perhydrophenanthrene with the cyclopentane ring is present. So, protostane has this kind of structures. Euphane has a 666, that is a combination of it's a tetracyclic ring with a 4 6-membered ring. Ursane has a 5 6-membered ring. Hopane has 4 6-membered ring and 1 5-membered ring. So, these are all the basic skeletons which are formed from squalene. So, these are all the divers. Here if you look at 6 and 5 combination, 6 only combination, another 6 only combination, another 6 and 5 combination. So, different complex structures are actually produced from a simple or a squalene unit. And here is a reaction which leads to a simple lanosterol molecule. So, the initial step is the squalene is converted to the squalene oxide. So, this is the most crucial initial step. So, once this squalene is converted to the squalene oxide under acidic conditions, what happens is like the enzyme actually folds the squalene oxide into chair and board conformation as shown here, and this leads to various shift of double bonds which leads to finally the lanosterol molecule after the elimination of water molecule. So, elimination of a proton. So this hydrogen is actually lost to give the double bond as shown here. And if you look at all this cyclisation, the initial step is the formation of the oxide, and this oxide is basically opened up to give the corresponding hydroxy unit, and this hydroxy unit actually leads to a carbocation, and the shift of double bonds actually takes the carbocation to this end, and from this other units are actually again few more shift of protons, and the shift of carbon at double bonds leads to the final lanosterol structure. The next one is the tetraterpene. So tetraterpene contains 8 isoprene units, and they have a general molecular formula C40H64, and the most common tetraterpenoid is basically the carotenoids, and these are basically fat soluble pigments. Pigment means these are basically colored materials. In fact, lycopene is shown here with the dark red color. So this is one of the colored substance, and many of these carotenoids have a unsaturated hydrocarbon like a lycopene. Here it is a conjugated structure. Due to the conjugated structure, it is highly colored substance, and they may also have the corresponding oxygenated analogues like xanthophylls. So this multiple double bond leads to a very strong color for these kind of compounds, and this leads to the pigmentation or the color of this tetraterpene. Here is another example. The lycopene when cyclized at both the terminals, so we have one terminal here, we have another terminal here. When these two terminals are cyclized, we actually end up with a 6-membered ring, the terminal cyclized structures. So the lycopene actually is converted to a beta carotene by simple cyclisation at the terminal. So we end up with a bicyclic system, and this again is a hydrocarbon, and this is also giving a very strong color. The next one is the polyterpenes. Polyterpenes and the polyterpenoid are basically the isoprenoid compounds where there are more than 8 isoprene units are actually present. If you look at the natural rubber is having a high molecular weight polymer, and here the isoprene unit are connected using a cis configuration. Gutta percha is another polyisoprene compound which is having a trans double bond. So these are all the two major types of polyterpenes which we encounter on a regular basis. And then finally we look at some of the irregular terpenoids. So the irregular terpenoids do not follow the isoprene rule. So here is an example. Ionones and damascones are basically the C13 nor isoprenoid compounds. These are formed by the metabolism or degradation of carotenoids. So here are the structures given here. We have all these compounds are called as terpenoid because they have a oxygen unit. So that means here in these kind of ionones we have a ketone unit. Similarly, damascone also has a ketone unit. So depending on the position of the double bond and the carbonyl unit, we have different sets of compounds. Another type is meroterpenes. These meroterpenes are basically secondary metabolites with the partial terpenoid skeleton. So they are not having the complete terpenoid structures, but they have partial terpenoid structures. When we talk about the tropalone sesquiterpenoids, they are actually substituted cycloheptane monoterpene. So this is a C7 unit, and they have some substitutions on the cycloheptane skeleton. So hinokitol is an example of a meroterpene, and these are basically formed even by the head to middle condensation of some of the isoprene unit. But generally when we talk about terpenes are formed by either head to head or tail to tail or head to tail combination, whereas meroterpene are formed even by head to middle condensation of isoprene. Totrol, musticinanthol are some of the examples of the meroterpenes. These are meroterpenoid compounds. Pisnidione is another compound which is formed by the head to middle condensation of the isoprene units, and these are some of the examples of meroterpenes. In summary, let us recap what we have studied so far. We have studied about the various classification of terpenes. We started off with the hemiterpene, and what is the C5 unit? That is the monomer unit that is responsible for the formation of all the terpenes. We have seen how the biosynthetic transformation of hemiterpene leads to higher terpenes. We have seen Monoterpenes are formed by the combination of two C5 units of hemiterpenes. Sesquiterpenes are having 3 C5 units. Diterpenes are having 4 isoprene units or C5 units. Sesterterpenes, triterpenes, tetraterpenes, polyterpenes all have higher number of C5 units. We also studied about the irregular terpenoids like ionones and damascene. We also studied about the monoterpenes. We elaborately studied the various biosynthetic pathways of the terpenyl cation, how the terpenyl cation can be converted to various monocyclic structures we have seen. We have also seen about how the squalene can be converted to lanosterol, and various other biosynthetic reactions also we have studied. With that, we conclude this session. Thank you.